All right, here on page 5, what I'd like you to do is work through this entire question on your own. The kind of guts are there. I put some fill in the blanks and just like on the last question. So most of what you need as far as structure is there to start with. So go ahead, pause the video, work through this, come back and take a look. As I look at this question, the level of dissolved oxygen in a stream or river is an important indicator of the water's ability to support aquatic life. A researcher measures the dissolved oxygen level at 15 randomly chosen locations along a stream. Here are the results in milligrams per liter. Do we have convincing evidence at the 5% significance level that the stream is at risk? Okay, so here's an example. There is a part A. You're like, oh, you said it's never always, but it does say convincing evidence. So I need to know to do a test here. So for the state step, I need to list the parameter, the hypotheses, the significance level. So the parameter is going to be mu, and this is going to be the true mean dissolved oxygen level in this stream. The null would be mu is equal to 5. The alternative would be they want to know, do we have evidence that the aquatic life is at risk? So a level below 5. So the alternative would be mu is less than 5 and alpha equals 0.05. Plan, random sample of 15. 15 is less than 10% of all stream locations. Normal large sample. Now, 15 is not bigger than 30. They didn't tell us the sampling or the population distribution was approximately normal, so we have to make a box plot. The way that I did this is I put all of this data into a list on my calculator. It's not in there, but I just want to rehash this with you. Once you have it in there, you go to second y equals, turn on the plot. That gives you the box plot with the dots. That's going to show you outliers if there are any. Whatever list, make sure that's selected where your data is, and then zoom 9. And then you can hit trace, and that's going to give you your 5-number summary by hitting the left and the right arrows. Again, this is not the correct data, but that's just how you do that. So I've put the box plot here for us. I'm looking for strong skewness or outliers, as we've talked about before. The AP exam is not going to give you a question where they fully expect you to do a test where the conditions haven't been met. So in this case, I would say the box plot shows no strong skewness or outliers. Therefore, the sampling distribution is going to be approximately normal. Conditions met, do a 1-sample t-test with 15 minus 1 or 14 degrees of freedom. So if I look at the answer key, box plot shows no strong skewness outliers, sampling distribution approximately normal. Conditions met, do a 1-sample t-test, 14 degrees of freedom. Okay, so pretty much verbatim what I said. Do summary statistics. You're going to have to get these from the calculator. Do you need all of them? Absolutely not. Let's just go through how to get them. After your data is in a list, you're going to click calculate. So stat, arrow over to calculate, 1 variable statistics, wherever your list is, make sure everything else is blank, calculate. You're looking for your sample mean and your sample standard deviation. Those are the 2 pieces of information you need here. So here, they told you the mean 4.771, standard deviation 0.94. So when I calculate my test statistic, it's going to be the statistic 4.771 minus the null value, the parameter, 5, divided by 0.94, divided by the square root of 15. I might as well just come over to the answer key here. So this is what the sampling distribution looks like. My test statistic is negative 0.94. And then with my p-value, I'm going to go second vars, TCDF, from a very large negative number to negative 0.94 with 14 degrees of freedom. I don't need to multiply this area by 2 because this is not a two-tailed test. So p-value is about 0.182 approximately. It is helpful to communicate TCDF and write that on your paper. It does not hurt. It takes about 5 seconds, but make sure you explicitly label this p-value. Conclusion. Because the p-value is greater than alpha equals 0.05, we fail to reject the null. We do not have convincing evidence that the true mean dissolved oxygen level in this stream is less than 5 milligrams per liter. So it doesn't look like the stream is at risk. Given your conclusion from part A, we failed to reject the null. Failed to is a type 2 error. So that's the only type of error we could have made. Type 1 error, we reject the null when the null is true. Type 2, we fail to reject the null when the alternative is true. So this is a type 2 error. That would be we don't find convincing evidence that the true mean DO level is less than 5 milligrams per liter when in fact it is. So the consequence of that was that the aquatic life is at risk, but we don't find evidence of that, and the aquatic life potentially doesn't continue on. All right, moving on to page 6. Okay. So let's take a look at this together. Check your understanding. According to a flyer created by BroadwayPartyRental.com, their 18-inch helium balloons fly on average for 32 hours. You purchase a simple random sample of 50 18-inch helium balloons from their company and record how long they fly. You would like to know if the actual mean flight time of all balloons differs from the advertised 32 hours. Okay, you could go ahead and do number 1 and number 2. 2 is going to be a little bit new, but I think you can handle that. So why don't you pause the video and fill out your solutions for number 1 and 2. So number 1, they said, does it differ? So this would be not equal to, and alpha is 0.05, we're assuming. Number 2, now they give us a confidence interval. And all I'm going to look at is my claimed value, 32. Does 32 fall in the 95% confidence interval of 28.5 to 31.4 or not? In this case, it does not. We had a test question like this on the Unit 8 exam, very similar concept. So based on this interval, what conclusion would you make about the hypotheses? Well, I would reject the null, and I would say because 32 is not in the 95% confidence interval, 28.5 to 31.4, I reject the null. We have convincing evidence that the true mean flight time for these balloons is different than 32 hours. In fact, it looks like it's less than, because our whole confidence interval is less than. So if we take a look at the solution here. Okay, filling this in, if the null value is in the interval, that means that null value is plausible, and we're going to fail to reject the null. And if the null value is not in the interval, which is what we just saw, that means that null value is not a plausible value, and we would reject that. So, summary, if you have a confidence interval, a C% confidence interval, say 95%, it's going to make the same decision as a two-tailed test with 1 minus 95% or 5% level of significance. But basically, the big takeaway is you need to be able to look at a confidence interval and a set of hypotheses and make a decision about the null and justify it. Is that null value in or not in the confidence interval? Be very explicit and always include the specific interval. Don't just say the interval. Like, include the specific lower bound, upper bound, and the confidence level. All right. So now we're going to move on to the last part of the lesson, which is dealing with a paired test. And if you remember back to Unit 4, we did matched pairs experimental design. And there were 2 scenarios where we came into a matched pairs design. One, you had 2 measurements on the same individual. So you had somebody, I think we talked about heart rate, standing and sitting heart rate, and you compare you to yourself. Or we paired 2 people up who are the same age, same sex, same height, same weight. They're very, very, very similar. We randomly assign one person to stand, one person to sit, and look at the difference between their standing and sitting heart rate. So that's where you're going to get paired data from. That's why we use this mu sub d. This is the mean difference. Okay? And the degrees of freedom is still n minus 1, but you'll notice n is the number of pairs. So if you have 10 pairs, you're going to end up with 20 sets of data points, like a before and after for 10 pairs. So it's just 10 minus 1. And when we talk about the normal large sample condition, you're just making one graph of the differences. And you're always using the differences. What is the mean difference? What is the standard deviation of the differences? So we move on to page 7 here. So we have this last question. And actually, I'm going to pause it and make a third video for this. This is going to get into the paired data, and this one's ran a little long.